Well, thank you, Andrew, for that introduction, and of course, to the Warrens for this highlight of my career so far. Happy to sign any book pages if you should still want. But also, I'm just so delighted to be here. So thank you for taking the time and being here and listening to this. So I have the privilege to talk about the wonder of science. And I think we really do not wonder at science enough. And that might be a strange claim, considering that we for sure live in a time where science has this real sort of pedigree that's seen as the arbiter of truth, and many people have a very expansive view of what science can do. But yet I think it's quite rare that we actually get sort of pulled out of ourselves and really find ourselves in a state of awe or wonder over a scientific discovery, or even over all the great past scientific discoveries that have made things like this conference possible. And that it often really takes stunning images, such as this one from the James Webb Space Telescope, to get us back into that place of wonder. So what I want to do before getting into the second part of this talk, which is on the limitations of science, is to give a very personal view of some of the things that I find wonderful about science. And I think when we think about the wonders or the goods of science, I think we often start with thinking about how science in different ways have helped us to further sort of human flourishing in different ways. And these are real goods. I mean, it's been a humongous contribution from science to human flourishing. And these are things that are sometimes, especially if you are sort of doing basic science like myself, are, I think, not really appreciated enough. But as Catholics, we are commanded to look also to the material well-being of our fellow brothers and sisters. We are commanded to feed the hungry. And thanks to science and the discoveries of things like dwarf wheat, we can today feed hundreds of millions of people that would otherwise be starving. We are commanded to heal the sick. And thanks to scientific discoveries of things like antibiotics, vaccines, and cancer treatments, which is illustrated here, we can do that again, like healing hundreds of millions of people from crippling disease or early death. And we are also commanded to teach the ignorant. And one of the great discoveries of sort of the past decades is that of information technology, which has enabled the spreading of information across the globe in just previously unimaginable ways. So the fruits of science are worthy of taking a back step and wondering at and finding yourself in awe of. But that is not what I'm going to be spending the rest of this talk on. Instead, I want to talk about what it is that is in some sense more fundamental good of science. And that is its amazing ability to figure out truths about the universe, about the material world around us. And we have already heard some of that. I want to start at the biggest scales. So we're talking about what the universe is like. We know today that it is a universe that's very dynamic, that had a beginning about 14 billion years ago in the Big Bang, and that then over billions of years have formed stars, galaxies, and even planets. And this is something that that has a real impact for how we see what kind of universe we live in. I mean, if we look back in time, we didn't always know that the universe was that dynamic. For a long time, it seemed like philosophy and the best science available was instead pointing towards a much more stable and static universe than the one that we now know that we inhabit. If we zoom in on our look at ourselves as living things, science have also revealed many truths of who we are as embodied creatures. And one of the things that I find really fascinating and awe-inspiring is that we now know that at the heart of life, we have DNA and RNA that encodes how an organism is put together. And first of all, I find it absolutely fascinating that that's sort of the heart of life, how nature so stitches life together is something like a language. Though as Catholics, maybe we should be less surprised about that, knowing how all things were created through the Word. But another thing that also tells us, when we look at not just ourselves, but all living things around us, is that this is not something, this is something that ties us together with all other living things. And that means that when we look back at saints like St. Francis, when he talked about Brother Wolf, he was not that far off. Science has told us the truth about how we are really tightly connected to the rest of creation. And one thing that I just can never get enough of is looking at, or like both contemplating and trying to imagine what's going on at sort of the smallest building blocks inside of us. And this is one of my favorite movies illustrating how a motor protein, so this is, think about it as this big molecule, is carrying material inside of a cell from one place to another. You could stare at it all the time, but this is going on inside of us all the time in trillions of cells. And something that's revealing about us is just how complicated and beautiful life is, but also the immense causal powers that it seems like all things have been imbued with, both in our bodies, so focusing on the small, and in the universe as a whole. So we have all these wonderful things. And the one thing that we can start asking ourselves is, why has the scientific project been so good at unraveling some of these fundamental truths about our history as well as about ourselves? And this is really just a transition to let me show one more picture from the James Webb Space Telescope, which is just beautiful. But it is a real, it's there also to remind me to talk about how this search for truth and beauty seem to often go together, which is one, I think, of the mysterious things when we look about how science works and why it works. So these kind of images are only possible because of the marvels of science. But it's also true that many scientists, when they try to get an intuition about going in one way or another, that you often find them saying things like they are guided by beauty. Sometimes in obvious ways, like with these beautiful pictures, and sometimes in ways that are more obscure for those who do not see beauty in equations the same ways as some physicists and mathematicians do. But that aside, I think it's good to together sort of look at what the scientific process is and thinking about why it works. So this is a sort of cartoon version of the scientific process that if you ever learned about sort of scientific process in high school, you probably saw something like this, that this is how you do science. And it is true, as we'll see, this is how you do science, even though we are going to have to make it a little bit more complicated as we go along. So a scientific inquiry starts with an inquiry, with a question. And it's a sunny day, so one of the things that we might ask is, what powers the sun? What makes the sun shine? Where does all that light and energy come from? And the next step is then to look into the question a bit more deeply. Maybe you measure how much energy is coming out of the sun. You design some device to measure just how much energy the sun is producing. And you also start looking into what are different ways to produce energy. This should then lead you to form a hypothesis. So this is a provisional answer to your initial question. And I mean, the sun looks kind of like a fire, so maybe your provisional answer is that the sun produces energy the same way as fires produce energy here on Earth, that is by breaking and forming chemical bonds. And the fourth step is then to design an experiment or an observation to test whether that provisional answer holds true or not. And in our case, probably what we would want to do is to figure out how many molecules you could possibly fit in the sun, knowing its size, and then see if that would, even in theory, provide enough energy to power the sun, this method you have come up with. And if you do that, what you will find that with the current energy output of the sun, the longest that you could power the sun with this sort of chemical, fiery energy is sort of thousands of years, maybe up to 100,000 of years. And we know that the sun has been around for almost 5 billion years, so we have demonstrated that our provisional answer was wrong. So we have falsified our theory. And it really just takes one such observation to show that our theory is wrong. So it's back to the drawing board. We need a new hypothesis. And we live in the atomic age. So maybe this time around, you think that, well, maybe the energy is coming from the fusion of atoms, following Einstein's famous E equals mc squared law. And if you do that, you do the same calculation, you will find that you could have the sun burning for 10 billion years without a problem. And you have now a scientific theory, maybe. Because it turns out that validating a hypothesis is not at all as strong of a conclusion as falsifying one. There's a real symmetry in this scientific process, which means that in some sense, all scientific truths are provisional, because there could be another hypothesis that fit the data as well. But not all scientific theories are as provisional as others. If we look at theories that have passed millions of tests, we would be very surprised if they failed the test the next day, and we'll probably would demand actually a few independent failings of the same test to really trust that we had broken the scientific theory. While on the other hand, if a failure is more expected, we might let it get away with sort of a simpler, maybe a single test. So 2 examples that we might consider is that general relativity is a big discovery of Einstein, which we'll have to come back to. It has passed millions of tests, and yet people are still devising astronomical observations to test it in new ways. Especially observations of black holes, if you have seen any of those. Part of the motivation there was to test general relativity. If we have, though, an expectation that something should be true, for example, we live in a solar system with many planets around its central star. Up until 25 years ago, we had never observed planets outside of the solar system, but we all sort of expected them to be there. So once we saw a single exoplanet around another star, pretty much all astronomers figured that the space was going to be full of planets. And that, of course, turned out to be true. And here I'm going to enter sort of a slight tangent, but just give you some idea of what this scientific process looks like in practice when we're talking about astrochemistry, since Andrew sort of gave you a teaser that you would learn something about what planet-forming disks and habitability and all the rest is. So a lot of my research interests have to do with these planets around other stars that we now know about. Many of them look like they could be similar to Earth, which raises the question of how often they have life on them, if any of them have life. And figuring out whether one of these planets could host life, well, one way to do it is to figure out how often they're formed with sort of the right molecules to have an origins of life happening. Now, to figure that out, we have to know something about how planets form. And this is a very brief introduction to how stars and planets form. In between stars, scientific observations have revealed that it's not empty space, even though it looks empty with our eyes. And instead, you have dust and gas that form these clouds. These interstellar clouds can start to collapse in on themselves. And that's how stars form. It's the gravitational collapse of one of these clouds. Now, when this collapse happens, it's not completely symmetrical, but you end up forming a disk at the center. And this disk is formed to preserve spin or angular momentum during the collapse. And that disk is where all planets form. So these are planet-forming disks. So that's where we would like to know what chemistry do we have there to understand how often do we form planets that might be able to, might be hospitable to life. Long before I entered astronomy, we had turned our telescopes towards the interstellar clouds and these like early stages of star formation and found that there are actually lots of organic molecules there. And I mean, I think this is worth on its own to take a step back, that we have the tools to actually figure out what molecules are hanging out around young stars hundreds of light years away is pretty awesome in its own right. But it doesn't stop there because we just don't want things to satisfy our sort of general curiosity, but we want to know how often do we have those kind of molecules present where planets are forming in these disks. And there are two ways that then we can go about setting up a hypothesis. The simplest one is to be, well, we see all these nice organic molecules, and some of you might recognize things like methanol, ethanol, dimethyl ether, in these sort of early stages of star formation. Maybe we just have the same molecules in these disks. Another way to set up the hypothesis is to go in the lab and see how do you form organic molecules in these very peculiar environments. And we have been doing both, but starting what we find out if we go into the lab. Well, one of the things we find out is that you cannot have any kind of normal organic chemistry in space. It's just too cold. You do not have a lot of organic reactions at 10 Kelvin above the 10 degrees or above the absolute zero. But you can have a very peculiar set of organic chemistry reaction, which starts with CO, this molecule, freezing out on an interstellar dust grain, and then having hydrogen atoms also landing on the grain, rattling around until it finds the CO. And if you continue to add more hydrogen atoms, let them rattle around, you soon form methanol. And you also have stars surroundings that can have some UV light that can break apart the initial organic molecule methanol that you form. And you can break it apart to form a couple of different pieces that can then be combined to form larger molecules like dimethyl ether and ethanol. These experiments suggest also that this should be present in disks. So now we have two different lines of evidence that we should find this kind of organic chemistry where planets are forming. And then came the observational test, which is that we turned our wonderful telescope, ALMA, which is sitting in Chile, in this very high altitude desert, and came online less than a decade ago. And what ALMA can do is to really find molecules in disks around young stars. And what it looks like when ALMA does that is that you see all these like nice, what maybe looks like blobs to you, but they're really beautiful disk portraits in emission coming from individual molecules. So each row here is a different disk, a different planet-forming disk. Each column is a different molecule where we have just isolated the light from a specific molecule. And you see these beautiful structures. And most of these are organic molecules. So there are plenty of organic molecules in these disks. But it's not the kind of molecules that we expected. It is not methanol, ethanol, dimethyl ether, all these oxygen-containing organics. Instead, they are nitrogen-rich and oxygen-poor, so-called nitriles. So falsifying all we thought we knew about organic chemistry, but actually very exciting for thinking about the origins of life, because it turns out these kind of molecules are among the most exciting ones to think about whether a planet is hospitable to life or not. So this is pretty close to how I described this sort of circle of the scientific process, how this actually unfolded in real life. We had a hypothesis, we falsified it, we're now coming up with new ones, why we see this very different chemistry in the disk compared to what we expected. And a couple of things that I want to draw your attention to is that this is very far from sort of a mechanical sort of knowledge machine that the scientific project is sometimes described at. There are multiple steps in this circle of the scientific process that are very subjective. Which questions you choose to ask, why we were even interested in finding these organic molecules, which was really due because of a deeper philosophical question of wanting to figure out if there's life in the universe. Why we come up with the kind of hypothesis that we do is a deeply mysterious thing. I mean, if you talk to scientists why they have a particular idea or hypothesis, I mean, they often say things such as, it was an inspiration. I mean, think about that. At the heart of what's supposed to be a hyper-rational process, you're basically calling on the Holy Spirit. I mean, this should give you some pause in thinking about science as a very different intellectual kind of process compared to other ways of finding truth. But there are other things that also complicates this process, especially if you have sort of an external pressure or an inward sort of ideological bent that is pushing you away from asking certain questions or pushing you away from accepting certain answers. There are many historical examples where, in hindsight, it seems like it took way too long for a certain idea to be accepted. I mean, a famous example, though full of historical sort of contingency, is that of heliocentrism, which I think we often end up focusing on Galileo. I think it's good to keep in mind that the originator was a Polish churchman, Copernicus, who did not face any opposition from the church when he originally proposed this idea. But here, of course, we do have a great heritage of the Aristotelian physics working in some sense very well to explain the universe we live in. And that means there's going to be a pretty high bar to introducing a new system like heliocentrism. A more recent one is the introduction of the Big Bang theory, which came about 100 years ago, as there were two very different scientific discoveries that were happening around the same time. One theoretical and one observational. So on the theoretical side, you had Albert Einstein coming up with general relativity, which reveals that the universe is sort of naturally dynamical. It's very difficult in general relativity to have a static universe. And one of the things that Einstein did, was to introduce the cosmological constant, sort of try to push it to be static. The other discovery was observational, which was Edwin Hubble discovering that galaxies that were further away looked redder. And one explanation of that is that they are moving away from us, they're moving away faster. So this is the same idea as an ambulance coming towards you has a higher pitch compared to an ambulance moving away from you. With light, you also get that compression if it looks bluer, if something is moving towards you, and you get things looking redder when they're moving away from you. Hubble, however, this is a slight tangent, died thinking that the universe was not expanding. So when we think about the discovery of the expansion of the universe as due to Hubble's observations, this is one of many examples where there's a big difference between the observations you make and the interpretations that you actually apply to them. Instead, it was, as Father Spitzer already introduced, the French physicist priest Father Lemaitre who realized that these two things together, the dynamical universe implied by general relativity and these observations of the red-shifted galaxies, that they imply that the universe was expanding. And then he famously took a step further and thought about, well, if it's currently expanding and you sort of roll back time, then you have to come to a point where the universe is so dense and hot that any kind of sort of normal laws of physics break down and you basically have a single quantum, or you have a quantum state. And then the universe expanded out of this, which is what became known in a derogatory sense as the Big Bang, and the name stuck. The Big Bang theory, though, took quite a few decades to be fully established after it was first introduced by Father Lemaitre, even though it was the theory that fit the evidence. And I think here it's interesting to sort of speculate why. Why did it take that long, even though it was by far the most natural explanation of what scientists were seeing? And on the one hand, I think what you had an increasingly sort of atheist scientific class that were the heirs of the Enlightenment kind of cosmology, where you have a universe that is the same both in time and space. And if you have an eternal universe, it is easier to forget that you need a creator. So when Father Lemaitre first introduced his theory, for many it just sounded too religious, which was given some an automatic sort of pushback against this idea. And I also can't help but wondering if Father Lemaitre, the reason that he had the idea instead of some of the other brilliant scientists that he was surrounded by, had something to do with his Catholicism. I mean, he already knew by faith that the universe had a beginning in time. And I can't help but wonder that that made it easier for him to sort of accept this idea, however it arose in his mind, while this idea might have come into many of his colleagues' minds as well, but they were, I think, would have been more prone to push it away than Father Lemaitre would have been, knowing already that this was in some sense a possibility. And I think there is a greater lesson there, which is that not only is science and religion not at odds with one another, but given that we know that truth cannot go against truth, and that when they sort of start overlapping, they must agree, I think we should feel quite confident that having sort of a true philosophy and a true religion should make it easier to make scientific discoveries and not the opposite. So we've already talked about sort of some of the human limitations of the scientific project, how it's a much messier kind of project than we often perceive, and how it has all these subjective steps. So it's really a kind of dialogue between the subjective scientist and the objective reality. I do want to talk some about these limitations. But before entering into that, I don't want you to leave this part of the talk thinking that because of these limitations, there's sort of something wrong with science or we can't trust it. Over time, it really does seem like science purifies our knowledge and really does does show us these great truths about the universe around us. And the reason it does that is because it is really a dialogue between the subjective and the objective. And good ideas and bad ideas are constantly tested against the objective truth. But back to the limitations. So there are several sort of classes of limitations of the scientific method. One of them is just what kind of questions are scientific? There are many questions about the universe that we can ask that are not scientific. That are still, at least seems to imply that there's some sort of knowledge. Things like, what do you learn from beautiful art? What makes art beautiful? What is the meaning of a piece like the Pietas? What did the people fleeing from as Vesuvius was having one of its great outbreaks, covering Pompeii? What did Jesus say to Peter? These are all asking questions about something that is true. Or if you have a moral question, what is the right thing to do? These are not things you could ever put in this sort of circle of science, even though there are sometimes, but I think less and less, ideas that you can use science to answer everything. But if you can't use science, then there's sort of a second idea, which I think is even worse, which is that only sort of scientific answers are real answers. You can only know if something is true if you can sort of demonstrate it scientifically. And this is something that really needs to be fought back on. And if there's anything that is important to do, I think both in our universities, but more generally, is to reclaim a trust in reason, that we can reason ourselves towards truths in many different ways, and science being one of them, that has been, as I say, very powerful for the material order, but is not at all suitable for many other objects, and that does not mean we should give up finding out the truth about them. Whether it's philosophy, theology, art criticism, or the testimony from someone telling them what their subjective experience was or what they heard. Those are all sources of truth and of knowledge. There is one sort of, so if we can't find out things, like we can't ask scientific questions about things like art and morals, it may be obvious that we cannot use science to prove or disprove things like God's existence. When you sometimes hear that science has been used to disprove God, that's a mistake in understanding who we mean by God, who is not in the universe, which is the purview of the material things in the universe, is generally the purview of science. God is, of course, neither material nor a being like a created being. So this is just a sort of quick reminder that this includes things that cannot be studied scientifically, includes God as well. That does not mean that we can never use science sort of as an additional tool towards learning something about someone. When you have a big moral question, let's say whether it is ethical or not to try out a product on animals, you can certainly use measurements to figure out things such as, does the animal seem to be suffering, for example? I mean, that would be a good piece of knowledge to have as you're making that moral decision. And the same thing, as we also heard from Father Spitzer, there are things in the created order that you can use to learn something about God, but you cannot use the scientific process to sort of make an ultimate call, does he exist or not? So these are all things that are immaterial, but does this mean that science, as soon as it's material, is sort of up to science to tell if it's true or not? Well, not really. There are many examples of things material, or things that happen in a material order, that are not up for grabs for the scientific method. One of them is miracles. It is not a scientific question whether Jesus walked on water or not. That is a historical question, which again is different from science. Or other times it can be a question of testimony. You can, of course, use science to purify miraculous claim, and the church frequently does that. But it's, again, very different from thinking that you can sort of disprove a true miracle. It is, however, also important to not to prescribe miracles to sort of scientific mysteries or difficulties. And one example of that is something like the origins of life. There's currently no good scientific theory of how the origins of life happened. This is a big, I would say, mystery of how that could have happened naturally. But that does not mean that it is a miracle. This is not something that, in principle, could not have a natural cause. And there is a good reason to continue to do research in things like origins of life and not to jump to a miracle until you have basically applied all the scientific ideas and tools that you possibly could. And that, I think, is also a way to avoid what otherwise might seem as a conflict between scientific laws on the one hand and miracles on the other. But not all origins can, in principle, be natural. There are origins that are in principle not up for grabs for the scientific method. The two that I would like to focus on are, on the one hand, the origin of the whole created material order. So this is not the same as the Big Bang. I mean, when we have the Big Bang, we already have something there that is sort of expanding and turning into the universe we recognize. But the Big Bang theory says nothing about where that initial state came from. And if that initial state was really the beginning of the material universe, then in principle it couldn't. Another, that is creation out of nothing, which only God can do. Another origin that cannot be scientifically tested is the origin of the human soul. This is also something that God creates out of nothing. And I think it's one of those things that can be quite, sometimes overwhelming to contemplate, that the whole universe and you are in some ways created in the same way. This is, one of the many gifts that God gives us. So there are many of these sort of limitations in terms of subject matter, what the scientific method can and cannot do. But I say the final limitation of science is that it is not self-sufficient. The scientific method relies on a lot of assumptions about both the cosmos around us as well as about who we are as humans that cannot be proven scientifically. The scientific project relies on there being order and intelligibility in the universe, which is not something that, again, science can prove that there is. It's something that it assumes there to be, that there are, in some sense, processes that are regular and orderly, that are there to discover and that are intelligible to us. It assumes that there is a correspondence between what I as a subject experience in the objective sort of world around us and what's really there, which is also not something that you can prove scientifically. And it does assume that we can trust our reason to tell the difference between something being true and something being false. And this is not something that sort of naturally comes out of a theory of evolution, for example, where if all we are sort of animals that are evolved to survive and procreate, there's no reason that should come with a reason that's finely attuned to finding truth. On the other hand, if our souls are patterned on God himself, we do have reason to trust in the scientific project. And that its faith that actually provides this sort of sure foundation that the scientific project really works and is a very effective way to uncover truths about the natural order or the material order around us. But I want to end with just a couple of brief reflections that are at the intersection between science and what you might say theology or philosophy. So all these limitations, as I said, should not at all be taken as science being not a wonderful tool and something that we should be very grateful that we have, but rather these limitations, in some sense, is why science works. And in its limited, when it's done right, in its limited scope, it has discovered amazing things about the universe that can help us, I think, to know something about the Creator and confirm some of the faith or some of the things we already know by faith. So one of the things the scientific project has discovered is, I said, what kind of universe that we live in. That we live in a universe that has a history. A universe that seems to actually be telling a story that has a beginning, a middle, and an end that's unfolding over time. There's a reason, I think, that many atheists were very concerned about the Big Bang theory as it was being presented. We also live in a universe that has an immense amount of intelligibility in it, that is order, that shows forth this sort of like organization on all different scales. And if we look back in something like the psalmists, what they tend to celebrate and see as evidence for God's presence is actually not miracles, but is this natural ordering of the cosmos. And we know that now so much better, and it's so much more impressive than we could ever, I think, have guessed without the scientific method. The scientific method has also revealed that the universe is full of these like sort of real causal powers, that you can turn cosmic dust into planets through the laws of physics, that you can have animals evolving from sort of lower animals to higher animals through the laws of biology. And I think we will one day figure out that we can have an ordinance of life happening out of chemistry. And this is, I think, shows an incredible generosity of the Creator in sharing his causal powers with creation, again in a way that I think would have been impossible to imagine in the pre-scientific world. So when we look at science and its wonders, those wonders are only made possible because of the limitations of the scientific project. But also those wonders should draw us out of ourselves and looking out not just towards the wonders themselves and towards the truths they reveal, but also towards the source of all truths and the ultimate creator of all things. And I think it's there where we start seeing the Big Bang not just as an amazing scientific discovery, but as an icon of what creation out of nothing looks like. Or when we start seeing icons of sort of like causal generosity in our little motor protein, I think it's there where we get this sort of like true, sort of really fruitful intersection of science and religion that the biggest wonders lie. And with that, thank you.